Okay, we're going to do dynamics now. So I'm just going to do example problems today. A couple of different sort of examples where we're going to combine relative motion with kinetic stuff. I think this is really cool, the kind of stuff you can do with relative motion. And then after that, we'll start moving towards rigid body dynamics. Everything we've done so far is particles. So, okay, here's the first example. So we have a pulley. And two masses connected to a cable. Let's say this one's 10 kilograms, this one's 5 kilograms. And first we're going to calculate if the ceiling is fixed. What's the acceleration vector of the 5 kilogram mass? And then second, that one doesn't use any relative motion. The second one does. So now what if that ceiling is accelerating? Like what if this contraption is in an elevator? What's going to happen when the elevator accelerates? So what's the acceleration of the 5 if the ceiling accelerates up at 2 meters per second squared? So you might just think, well, so think about what's going to happen here. This is the light one, this is the heavy one. So the light one is going to accelerate up, the heavy one's going to accelerate down if there's no acceleration. And at first glance, you might just think, okay, well, if the ceiling is accelerated now, whatever we get for the upward acceleration of the 5 before it accelerates, we're just going to add 2 meters per second squared to that. That might be, a reasonable assumption. I mean, the basic motion is still the same, but the whole thing is accelerating up. But that's not what happens. And in fact, well, any of you guys in modern physics right now? It's called modern physics. No. No, that's called archaic physics. Outdated physics. No, not really. Relativity says that, general relativity says that all reference frames are equal. This is very different than the way we think about it in classical physics, but all reference frames are equal, and there's no way to tell whether your coordinate system is accelerating or whether you have a gravitational field. There's no way to make a distinction between those two. And so when this is accelerating upwards, what you can think of it as equivalent to having a stronger gravitational field. And so it would behave as if there was a stronger gravitational field there. That's not how we think about it in classical physics. We think about inertial reference frames. An accelerating coordinate system is fundamentally different than a non-accelerating. But you should bring that up to Tony. Try to trick him. Bring this problem up. Tell him that you learned in dynamics that in this accelerating reference frame, you could actually tell from your measurements that this reference frame is accelerating. You know what I mean? Oh, that's why I want you to do it. Okay. So the first one, and then tell them you're going on vacation. Okay, so first of all, free body diagram. We're just going to do free body diagrams of each of these two objects. So the 10, there's a weight of 9.81 times 10, 98.1. There's an upward force, T. And so Newton's second law says 0T plus 0, negative 98.1, is equal to the mass, 10, times the acceleration. And we can tell pretty easily from this that the acceleration is going to be down, but we're not even going to mess with that. You'd never have to make that prediction. The only thing we have to notice is that the acceleration is going to be vertical. So I'm just going to write this as 0, A, 10. Okay, acceleration at 10. So we have two equations there. Well, one is useless, 0 equals 0. Hopefully you already learned that in one of your previous classes. But we have this useful equation that says T minus 10A10 is equal to 98.1. I'll set that aside. We can't solve it because that's one equation, two variables. And then free body diagram of the 5. Downward force of 49.05. Upward force of T, because that's the same cable. Assumptions are we making to assume that cable? We're frictionless pulley. We are going to assume that it doesn't stretch. Massless pulley and massless cable. That seems like a lot of assumptions, but usually you get pretty good results with that. Yes, that's right. That's what you're hoping. Although after we do rigid bodies, we'll be able to, this is going to be sort of a cool thing, I think, because in all your classes so far, you've assumed that pulleys are massless. Dealing with friction is pretty easy, but dealing with like, oh, well, how would it affect it if the pulley had mass? We'll be able to do that calculation and actually see that difference. But most of the time, you choose your pulleys and your cables based on them having small masses and etc., friction related to the other forces you're dealing with anyways. So Newton's second law says 0T plus 0, negative 49.05 is equal to 5 times the acceleration of this one, which is, I'll call it 0A5. And that gives us a second useful equation that says T minus 5A5 is equal to 49.05. That's two equations for three variables. So we can't solve it yet. But then if you notice that this is where we use the fact that the cable is inextensible. If you assume that cable keeps the same length, and if you pull the 10 kilogram box down an inch, this one goes up an inch. And so there's the velocities have that same equal and opposite relationship, and the accelerations have that same one. A10 is negative A5, yep. So one's going up and one's going down, but the magnitudes are the same. So I'm going to call this a geometric constraint equation. this idea is going to come up in a lot of contexts. And that equation 3 says, so A10 is negative A5, and so I'll write that in this form with all the variables on the left and the constant alone on the right as A10 plus A5 is equal to 0. So now we have, I'm going to write out this matrix, equations 1, 2, and 3. And our variables are T, A5, A10, and then the constant on the right side. So equation 1 says 1 times T minus 10 times A10 is equal to positive 98.1. And then equation 2 says 1 times T minus 5 times A5 is equal to 49.05. And then equation 3 says 1 times A5 plus 1 times A10 is equal to 0. Can someone calculate that? Or preferably two people. And okay, so A10 is negative 3.27. A5 is positive 3.27. This is newtons, meters per second squared, meters per second squared. One thing I want you to notice here is statics. So in this case, I guess it's maybe kind of obvious that the easy way of approaching this wouldn't work. You have things hanging on the two different sides and both of the weights are 0. But one bad habit that you get out of statics, that it's easy to get out of statics, is if you see a mass hanging from a cable in statics, the tension in the cable is just the weight of the mass. In dynamics, that's not true anymore because the mass times the acceleration adjusts that. Okay, so you can see that here. The tension in the cable was 65 newtons. That's not either of these two weights. It's somewhere in between them, I guess. Okay, so part B. Now this is the sort of weird one. This is like, we'll see that if you think about it in terms of relative motion, it's pretty easy to think through. But this one is kind of like a brain teaser, you know. And it actually has the name Atwood machine. I don't know any of the history of thinking about that or whatever, but it's a cool enough problem that it has its own name. And so let's say that what we want to calculate is the acceleration of the 5 relative to the ceiling. Okay. So imagine that this is on an elevator, you know, and you're doing this calculation, and we're going to calculate if there was a camera attached to the elevator, what acceleration of that 5 kilogram mass would that camera see? Okay, and what we're going to see is that camera would see something different when the elevator was at rest or not accelerating than it would when the elevator is accelerating. What do you think? Do you have intuition about that? So when this elevator, if this elevator is accelerating up at 2 meters per second squared, is the absolute value of this acceleration going to get bigger or smaller? I think it's going to get bigger. I don't really remember. We'll calculate. I think it's going to get bigger because it's like the effect of more gravity, and if you have more gravity, that's going to accelerate more.
Where are we looking at? Are we looking at the 5 kilogram or the 10 kilogram?
Well, we're looking at the 5 going up just arbitrarily, but the 10 is going to go down the same amount. Okay, so first of all, why wouldn't this problem be exactly the same? Like what changes? Do those free body diagrams change? Well, okay, so we're doing it in terms of accelerations. If you were doing it with a like relative, you know, then yes, you could treat it as a gravitational field. But for us, the way we think about it, those weights are still the same. The tensions are still the same. So the free body diagrams don't change. So what does change? That's getting at the right thing. The way to think about it is just you can't use Newton for classical approaches. What we're using, Newton's second law only applies if your coordinate system is inertial. Okay, so we just simply can't approach it this way because we're not allowed to use Newton's second law if our accelerations come from a camera on an accelerating elevator. Who's with me on that? Anyone? Who stopped listening a long time ago?
Well, as of last night, I did.
Hunter. Damn it, Hunter. What?
As of last night, I did.
Okay. Oh, yeah, that's true. Okay, well, so what do we have to do in order to use Newton's second law? Because that's the only tool we have in particle kinetics. Yeah, but we don't have any more laws. But we just have to use the relative motion equations so that we can do this problem in an inertial coordinate system. And so we need to use an inertial coordinate system. And so I'm going to call the true acceleration of A5, let's say the acceleration of 5 relative to the ground is equal to the acceleration of 5 relative to the elevator plus the acceleration of the elevator relative to the ground. And the acceleration of the 10 relative to the ground is equal to the acceleration of the 10 relative to the elevator plus the acceleration of the elevator relative to the ground. These two equations as separate issues? Yeah. So what we're going to do is we can use in Newton's second law. And then these other ones, we're going to see that to use the constraint equation, we have to talk about it in terms of these other ones. Okay, yes? Those are all like vector components, so they're sort of halfway in between. Okay, so free body diagrams are the same. So Newton's second law for the 10 kilogram says 0t plus 0 negative 98.1 is equal to 10 times no x acceleration. And the y acceleration is, okay, we're going to break up into these two. So a 10 relative to the elevator plus elevator relative to the ground. And this is just given in the problem. This is just positive 2. So our first useful equation says t minus 10, bless you, 10, a 10 relative to the elevator is equal to 118.1, right? With me on that? And then Newton's second law for the 5 is 0t plus 0 negative 49.05 is equal to 5 times 0, and then for the y component, a of 5 relative to the elevator plus acceleration of the elevator relative to the ground. And this one's still 2. So our second equation says t minus 5 times the acceleration of the 5 relative to the elevator is equal to 59.05. Okay, so we have 2 equations for 3 variables. We're going to use this constraint idea again. And what does the constraint look like in this case? So there's still some viewpoint where if you pull the 10 kilogram down an inch, the 5 kilogram goes up an inch. So what's the relationship there? Is it in the ground frame that makes sense, or in the elevator frame? Elevator, yep. So we have A10 is equal to negative A5. And so our third equation says A5 plus A10 is equal to 0. Yeah. One, two, three. The variables are t, a5, a10, and then the constant. So for the first one, we had 1 times t minus 10 times a10 is equal to 118.1. The second one, we have 1 times t minus 5 times a5 is equal to 59.05. And then the constraint says these are relative to the elevator. 1 times a5 plus 1 times a10 is equal to 0. Can a couple people calculate that? Okay, so t is 78.73. Okay, so a5 relative to the elevator is 3.97. 94. And then acceleration of the 10 relative to the elevator is negative 3.94. And then if you wanted to calculate the acceleration of each of those relative to the ground, you could using the relative motion equation. But this is the one that shows the sort of interesting part about this problem. It says that if you have those two masses and you're on an elevator, or say it's not you, you're watching a video, and you use that video to measure accelerations of those two things, you can tell whether the elevator is accelerating or not. That's cool, right? Come on, it's cool. Yeah.
They're called eyes.
Yeah, right. This is a camera. Okay, so so we, because we're doing classical calculations, would say that you can tell that the elevator is accelerating based on those accelerations. Somebody like special relativity would say you can tell that either it's accelerating or the gravitational field is stronger. Okay. Let's do another one like that. It increased. It was 3.27 before.
Oh, yeah.
Oh, I see what you mean. Yeah. The magnitude is increasing. So let's say this is 10 kilograms. Let's say this is 5 kilograms. Let's say there's a coefficient of friction of 0.1, and that at this instant these are moving this way. So that lets us know, that's the velocity direction. That lets us know what direction the friction force is acting. So let's say that this structure is at rest, you know, the floor, whatever that, what would that be called? Surface? Yeah, well, I already wrote floor. The floor is at rest. And then for the second one, we'll say the floor is accelerating down at 2 meters per second squared. And in both cases, you know, we want to calculate the acceleration of the 5 kilogram box. And I guess really we want it relative to the floor in both cases. Okay, so free body diagram of the 5 kilogram box. There's a cable tension. There's a weight of 49.05. There's a normal force. I'll call that N5. Well, I guess that's the only normal, isn't it? So N. And then the friction force is opposite the velocity, so that's going to the left with a magnitude of 0.1 N. Newton's second law says 0T plus negative 0.1. Yes, it would. Thank you. The friction force, negative 0.1 N 0. The normal force is 0 N. The weight force is 0, negative 49.05. 2, 3, 4. And then what do we know about the acceleration? It's, yeah, in the x direction, so I'll call this A5, 0. The y equation says n is equal to 49.05. The x equation says t minus 0.1 times this, so minus 4.905 plus u is equal to 5a5. And so I'll keep one equation from this that says t minus 5a5 is equal to 4.905. And then the hanging mass, free body diagram. There's a weight of 98.1, an upward force of T, and so Newton's second law says 0T plus 0, negative 98.1 is equal to 10, and then 0, A10. So our second useful equation says T minus 10, A10 is equal to 98.1. And then the constraint equation, this is two equations for three variables. So our constraint equation, well, if the sliding one moves an inch in the x direction, where does this one move in the y direction? Down. Oh. And so, no. So A5 is equal to negative A10. And our third equation says A5 plus A10 is equal to 0.
So can we say the constraint equation essentially net force?
The constraint equation is just a geometric thing that says, since we're assuming that this cable doesn't stretch, moving one this way has to do this thing to the other one. That would just be, no, don't think of it that way. Just think of it as like geometry, because those will come up to be all sorts of things if you add more pulleys and stuff. Okay, so equation 1, 2, 3, and then T, A5, A10, and the constant. So equation 1 says 1T minus 5A5, and then the constant is 4.905. Equation 2 says 1T minus 10A5 minus 10A10. And the constant is 98.1. And then equation 3 says 1A5 plus 1A10 is equal to 0. And a couple people calculate that. 35.97. 6.20, 21, and negative 6.21. Any questions about that one? Okay, so now we're going to do the same thing with that surface accelerating. You think that acceleration is going to get bigger or smaller? It is going to make the friction go up, but I think it's going to be bigger too. But actually, I think there's two. In this case, there are two competing effects. It's going to make this have more. It's going to make the normal force go up here, which is going to increase the friction, and it's going to make the weight go up on this, which is going to pull it down more. Well, let's see. Yep. Oh, it's accelerating down. I'm sorry. Yeah, it is accelerating down. So everything I said was backwards. So it's going to make this friction force get smaller, and it's going to make that force get. No, it's going to make friction force gets smaller. That force gets smaller.
There is no friction force on it.
Right. But the thing that's making the whole thing accelerate is the weight, and the weight is getting less. The sort of equivalent weight is getting less, anyways, let's just do it because I think there's two things happening in the opposite, that work in the opposite direction. So free body diagram of the 5. There's the weight of 49.05. There's the cable tension. There's a normal force and a friction force of 0.1 times the normal. We're going to call the acceleration of, so the acceleration of 5 relative to the ground as a vector is equal to the acceleration of 5 relative to the elevator plus the acceleration of the elevator. It's not an elevator anymore. I call it floor. Acceleration of the floor relative to the ground. And the acceleration of the floor relative to the ground is 0, -2. So Newton's second law says T0 plus 0, -49.05 plus -0.1 n is equal to 5 times A5 relative to the floor, -2. Any questions about that? So the y equation says n is equal to 47.05. So the x equation says t minus 4.705 is equal to 5 A5 relative to the floor. Oh, -10, thank you. So 39.05, and this is 3.905. And so the first equation that I'll keep says T minus 5 A5 relative to the floor is equal to 3.905. And then the hanging mass has a weight of 98.1 and upward force T. And the acceleration of the 10 relative to the ground is equal to the acceleration of the 10 relative to the floor plus the acceleration of the floor relative to the ground. And this one is 0, -2. So Newton's second law says 0t plus 0, -98.1 is equal to 10 times 0 for x and A10 relative to f minus 2. And so equation 2 says t minus 10 A10 relative to f is equal to positive 78.1. Three equations, two variables. So we need a constraint equation. And the constraint equation is that, our third equation says A5 relative to the floor plus A10 relative to the floor is equal to 0. And the same reasoning is in part A. So that's equation 1, 2, and 3. And the variables are t, A5 relative to the floor, A10 relative to the floor, and constant. So from equation 1, we had 1t minus 5 times A5 relative to the floor. And then the constant is 3.905. Equation 2 says 1t minus 10 A10 relative to the floor is equal to 78.1. And then the constraint says 1A5 relative to F plus 1A10 relative to F is equal to 0. Could a couple people calculate that for the tension? 4.95. And so A10 is a relative to the floor, 4.95 negative. Okay, so this time the surface was accelerating down. It has intuitively the same effect as decreasing the gravitational field. And so you got a lower tension and a lower acceleration. Pretty cool, right? That's what I was afraid of, but I felt like we had to cover this anyways. Okay, see you Wednesday.